Hey guys, how's it going? So today actually we're going to be covering BERT. Essentially, BERT is a bidirectional encoder representations from transformer. It was a paper introduced by Google researchers in 2018. So essentially, it's a pre-training method for NLP models, right? So today the goal essentially is to kind of like go through the code line by line and explain each everything in such a way that you get to understand how these models work, right? So I'm not going to cover the paper because I feel like the main ideas essentially will be visible in this code, so you will be able to understand actually what the paper was all about anyway. So however, I think it will be great if I kind of like skim you through like some of the ideas at the high level before we get into the code. So we can think of like the key innovation around BERT at that time of the paper when it was published was the use of bidirectional transformer in the pre-training stage, which allowed the model to essentially capture context from left and right side of the sequence of the weights. I use the word innovation mainly because of at that time we were using LSTM. So LSTM were not bidirectional by default. So essentially they had to process input sequence in one direction from the beginning to the end, right? So hence like they're called BERT, like bidirectional encoder representation from transformer, right? So the second point from the paper was that the pre-training involved training the model on large corpus of text using two methods, which was the mask language modeling and the next sentence prediction, right? And this code here on the data set will show you how we transform the data to kind of like achieve these two things. So at the high level, you can think of mask language modeling as like we randomly mask some token input sequence, and the model is trained to predict the original weight from the surrounding context. Okay, then the next sentence prediction, on the other hand, involved predicting whether two sentences are consecutive or not, right? Which helps the model to understand the relationship between different sentences. So you will see that we break paragraphs into sentences, and we're gonna try to um, match some of the sentences correctly, and some we're gonna match them incorrectly. This is just because we want the model to learn if like the second sentence is the correct or not, right? So that's what the next sentence prediction. That's the purpose of the next prediction sentence, right? So BERT is still widely used today, even if though I said 2018 this paper was produced, they are still widely used today and it achieves state of the art in many NLP tasks. This include name identity recognition, question answering, and some of the modern systems are built upon BERT. This include retrieval systems and stuff like that. So yeah, I think we're gonna learn a lot, and I'll try to make sure that I hold your hands throughout this code and make sure that I explain each line of code in such a way that you understand how everything works. So by the end of the video, at least you will be able to understand how this model work and how the code works also. So yeah, without wasting any time, let's get into it. So now coming to the code, what we have here is that we importing these libraries. So random essentially is going to help us to randomly generate values. Then we have a typing, which is essentially going to help us to provide support for typings, which are annotation used to specify expected types of functions and arguments. Then we have collections. So this is going to be handy, especially when we get to the tokenization state of weights. But it's essentially it's going to give us the frequency of each word. So you can think of like we have a sentence, right? And then have to we're gonna have to count the number of words in that sentence, like number of words that are occurring, something like that, right? So let's say, for example, there can occur 5 times or something like that, right? So essentially, counter is going to help us do that. Then we have the path. So you can think of path as it's an interface for working with file systems, right? So we're going to use it, especially when we store or we try to retrieve data set. Then NumPy is going to help us to do some sort of like matrix multiplication, and pandas is going to help us to wrangle the data and manipulate the data and create columns and shape the data in such a way that we can actually be able to understand it, right? By that I mean we can create columns, right? And columns are readable, and we can see what this column meant and what it contains. Then we're going to use touch, which is going to help us to create uh, tensors and models and stuff like that. So we're going to see how it works also. Then you can think of TQDM as like it provides us the progress bar of how long the running task will take. Then we have a data set, which will help us be able to get the data. Then we have the vocab and the get tokenizer. So I'll show you how these libraries are getting used, right? So here, this code is just to say that we want to use GPU if it's there, else we want to just make it to be a CPU, right? So very handy tool. So here we have these special tokens. We call these special tokens. So their purpose essentially, you can think, for instance, let's say we have let's say we have an input to our model, right? And the model takes a fixed input. For example, let's say it takes like 50 tokens, for instance, right? So you can think um, of tokens as like individual weights, right? They can mean different things, especially if you're using like different tokenization algorithms or byte pair or something like that. But for now, let's just assume that okay, tokens in this case is just like weights, right? Like it's just a weight. So let's say this case, when I said 50, it means that we have 50 tokens. So now, let's say our sentence that we have currently, and we have to push it to a model, it has like 30 tokens, like it's a sentence with 30 words. So you can see that it's not 50. So how do we get it to 50? We use this paired. So paired, essentially, we're going to pair the sequence. We're going to add these paired. So we're going to add this paired, maybe times 20. So when we do that, we're going to be able to get to 50, right? And that's when then now we have a same length which is expected. So that's what we're gonna do. Then this sequence, you can think of it as like we have the first sentence, right? We have a first sentence and we have the second sentence. Then what we do is that we separate them with this special tokens, and we're gonna put it in the middle here to say, okay, that's how we separate this, right? Then we have a mask. So you can think of mask as like we have uh, like let's say we have a sentence like subscribe to data driven. So what we do is that we take this sentence and we're going to mask this. For example, let's say we mask two, then we mask two with this, right? We use this special token. So then the model will then use the context bidirectionally, so looking at the left and right ways and to try to predict this, right? So that's what we're going to do. And if the words, some of the words are out of cup, meaning that they were not seen, then we're going to use this word unknown. Okay. Then we have mask percentage, which is essentially what it means is that given a sentence like so, essentially what we're gonna do is that we're gonna mask 15%. Given the length of the sentence, we're gonna mask 15%, right? So which means that given a sentence like so, we're gonna mask 15% of that, right? So that's what this is a more like a hyperparameter that we state, right? And we're creating these columns which are gonna become handy so that we know given a data set, which is a next token and which is not a next token, right? So that's what these columns are gonna be helping us with. Um, we create we read in the data here from given the path. The path, like I said, it's like more like a working with file system. So it's gonna tell us that okay, at this directory there's this data set, and when we read it, that data set is a CSV file, which is a data set about movies and it has reviews. So we want the column called reviews from that data. That's the only column that we want. And we're gonna convert this into a series. So you can think of a series in pandas as a one-dimensional array. I think that's like the better way I kind of like look at it. But yeah, it's gonna give us a series. Then what we're gonna do is that we have this ds from and ds2. So essentially this actually, you know what, let me not pass this because I don't know if some of you understand this in much detail. So I think I just want to spend some time just to kind of like explain to you. So like I said, we're going to use this example so that I explain to you. Uh, yeah, like I said, I don't want to pass in the code. just to make assumptions. So essentially, a series. Let's say we have we imported pandas, right? So let's say we have some sort of like sentences. So I'm gonna say sentences. So let's say we have sentences. So essentially, when we get a sentence, we get it as a paragraph. Then we're gonna convert it into like we get it as a paragraph. We're gonna convert it into sentences. So you can think of here we have a list of sentences. So maybe I have a cat named Bob. Then we gonna say I have a dog named uh, Tom, for example. Uh, then what we do is that we're gonna have NSP labels, which is gonna tell us if like these next sentence prediction. So we have labels, and we're gonna say so, then it's gonna be next and not next. So this essentially, like I said, the next sentence prediction tell us if you're next or not same or not next, right? So what we do there is that we reading the the sentences or the reviews. So let me say pd dot data frame. We're gonna take in the sentences. So I'm gonna call this sentence. Then I'm gonna call this sentence. Okay. Then we're gonna say NSP class. Then we're gonna pass that, and we're gonna run this. So as you can see, that's what we're gonna do with like that next sentence prediction. So uh, that's what it is, right? So, but now, what is a series? So now, let's call this movie reviews. So, for example, movie reviews. So let's say we have movie reviews like so. So we can say this is our table like so. Then we can convert this table and take table pd dot series. So I just want you guys to have a understanding of like how series works. Oops. Table. Then we're gonna take in the column called movie reviews. So just to avoid bugs. Okay, this is I'm gonna paste it here. I'm gonna print out the table. So this is how the series works. So it's a one-dimensional. So you can see this is how the data when we were here. This is how the data will be transformed. This is how we get the data. So you can think of like we have so many paragraphs here lining up, right? So this is what we did. We get. So I'm doing this. The reason I'm doing this is because when I go through the code, I want you to have a picture, like what kind of like things we're doing, like right. So this way you get to understand and get to have a deeper understanding of like how this thing works, right? So here, what we're doing essentially is that we are filtering the data. So we are saying that if ds from is not null and ds2 is not none, then we want to filter our data. So you can think of like we have a 1 million data. Then we are saying that we want to select the data from this or to this. So we can think of this as like we are subsetting. So it's like, no, that's what we do. So, but that's what you should know. This code is just subset. We have a million of data and we don't want to train all of it. We want to select a subset of it, right? Then here we're gonna get the tokenizer, which is gonna help us tokenize. Then we have the counter, uh, which will count the frequency of weight. Then we have the vocab. Okay. Um, then here we have the optimal sentence length. So essentially, you can think of this as like uh, it's going to determine like what is the given the sentences in our data set, right? We're going to use probability to determine like what is the optimal sentence length within this. So this way we get to like we don't just give like a sentence, right? Like we don't just give a random number just like that. From our data set of reviews, what is a like an optimal sentence from reviews, right? So that's what we do. We're looking at all of these reviews and we try to come up with a good number. So that's what we're gonna include. Then we have show include text. So here, it should include text. It's just for debugging purposes. So essentially, if like it should include text, then we include mask, sentence, and sentence. And these are essentially columns that we create. So we're gonna use these columns as we go on, right? And here, you don't have to include them, especially if you're not debugging. You don't have to include this, right? Just can use this. As you can see, these are all these functions, all of these are columns that we defined right here, right? Then we call it this function. Now we're gonna get into interesting things now. Like this is where the interesting stuff are gonna start, right? So we have prepared data set. So let's go to this function. So the prepare, the first thing that we do is that we firstly initialize the sentence, which is going to hold all the sentence within our data set. And this is also going to hold the next sentence prediction. Then we have the sentence length, which is going to hold the length of each sentence so that we can be able to calculate the optimal sentence for all the entire data set. Okay, so what we do here is that we loop through all their review. So you can think of like if we go to example, so we're going through each review. So you can think of here we have a paragraphs of reviews and we're going through all of them. Okay. Then what we do is that we say review that split. So here when we split the review, we get reviews sentence. Okay. So, like I said, a review can be a paragraph, right? Someone can write as much as they want, right? Like that's why here we have to say it's not a necessary sentence yet. So here, when we split this, we get the sentences from that review. I hope I'm not confusing you, right? So you can think of this as a list now holding those sentences, right? And then we get those sentences and we add them inside the sentence list. Okay, so I know this might be confusing. So let's take an example, right? So I think this way might be easy to crack. So I'm just gonna remove this example. So I'm gonna say review. I'm just gonna use the same words as we're using. So I'm just gonna paste this paragraph here, right? Uh, this is mainly because so I'm just gonna use this so that I can be able to use this paragraph across all the lines. So do this. So you can think of this as like a review. Just look at it as a review, right? We have a this review. So what we do here is that the first loop get a review and we're saying review that split. So let's copy this and see what it does. So essentially this is gonna split the words because our intuition is that each sentence is split by where there's a full stop, right? Uh, then there's a space, then they start a new sentence. That's our assumption. So that's why here we're doing this. We say review. Now you're gonna see we have these sentences. You see, we have these sentences. If you look closely, you will see that Sarah had run and they start a new sentence, and this is a new sentence. She walked all the way, right? And we start a new sentence. Then here, what we do is that we add all these sentences, we add them to sentences, right? So we're not adding the list, right? I repeat, we're not adding the list, rather we're adding, this is not going to contain a list. That's what I'm saying. This is not just going to contain the list of sentences, but the sentences themselves, right? So let me say sentence. I'm just going to do that. Then what we do is that I'm just going to take this sentence, okay? And what I'll do is that I'm just going to say plus equals to this. And just print the sentence. You see what we happened is that even if we had multiple of these, even if we had multiple of sentence list, as we keep on adding them to this sentence, we're not adding them as a list. We're adding them as like sentence like so. So essentially, what I'm saying is that this might look odd if you're coming from a different language. So essentially, when we add this list, they're gonna be sentences inside here. So it's gonna be strings. It's gonna be strings, even though we were adding, even though it looks like we're adding list. Okay, so I just that's one thing that I want you to know. So and what we do is that we take in the sentence length, uh, which is which was a hyperparameter if I'm not mistaken. Uh, did I miss that? We have sentence length, which is the list. Then we have review sentences. So here, essentially, what we're doing is that we're taking all the sentences within our paragraph, right? We take that, then we have the sentence length. Then what does this do? So it says a self update length. So let's go to this function. So this is it, right? So we see here what it does is that we're getting the sentences. Yes, I repeat, here we said that we have review sentences. So we're getting a list of sentences, of right? That's what we saw. We saw this here. We're getting a list of sentences, right? Then when we get here, we loop through a list of sentences. Okay, then we get each sentence and we calculate the length of that. Okay, then we get the length and we say length dot append, then we return the length. So this will just make sense, right? Because just to kind of like show you from a practical point, so what we do is that we give this list to that function that we saw now. Then what we do is that we get this, right? And we calculate the length because of we want to know like the length of the sentence. Remember that the goal is to find the optimal length, right? Then what we're gonna do is that we're gonna calculate for all of these. We're gonna calculate their length. We're gonna calculate their length, and then we upload each of these length inside here, inside the length, right? So we see this length here is this sequence length. You see, so for each review, we're gonna have to do that. So you can see that this code is gonna run, especially if we have a lot of reviews, right? So, but that's that because we have another full loop here. But that's the main goal, right? Then here what we do is that we say self find optimal sentence length. So now you might be asking yourself, but what does this do, right? What's the purpose of this? So here this function is to find the optimal sentence given the sentences of all the sentence in the data set. We want to find the optimal sentence. So but your question now is like, yeah, I do get that, but how does it work, right? So what we work is that we use percentiles to do that. So we're gonna take the length and we're gonna convert them into array. Then we use np.percentile. Then this is gonna generate the given the whole entire data set, what is the optimal sentence, right? Sentence length that we can use. Then we're gonna use that as our as our sentence length in our data set. Where are we? Where are we? Where are we? Okay, we were here. So I hope we understood this, right? I'm gonna repeat. So we go through the data set, we get the reviews. We don't know if review is a sentence, the paragraph, we're getting it, but it's a paragraph, right? So what we do is that we split it, then we get the sentences, right? We get the sentence in a list, right? Then we add this to the sentence. So we add those individual sentence. Yes, we add them to the sentence. So you can think of this guy as holding all the sentences for all the entire data set. Then we update the length of this sentence length because of we keep on updating it, right? Then we find the optimal sentence length using the percentile, right? Then now we have this thing called for cup, right? So what we're gonna do is that we're gonna go through the sentences. So you can think of like we're getting each sentence in that. Then we say self the tokenizer. So this essentially is gonna it's gonna tokenize the the sentence and it's gonna give us weights, right? So then we use this counter to update this counter. So you're gonna think of this counter essentially as like we counting the frequency of each weight, right? So so You know what? Let's just do this. Let me just make an example, right? I think it will make sense. It will make sense now in a second. So what I'll do is that I'll try to, because I think it does not make sense for me to walk through this code, but then they don't make sense, right? So I think it's better if like I explain each line of code, so that even if like we get far together, like you understand like each where we are. So where are we? Where are we? Where are we? We're still here, right? So so what we wanna do is that we're gonna initialize the tokenizer. This is what we did here, right? So I'm gonna say get tokenizer, and I'm gonna, because I'm gonna show you what this stuff does, right? So then we we gonna use it here. So we're here, right? So we said we're gonna take the sentence and we're gonna tokenize it. So I want you to see what we're getting. So we're gonna take the tokenizer and we pass in the sentence. So what's that sentence? We can copy this, it's fine. And we wanna print this out. Okay. So I think it might take a while because I haven't uploaded this, so it's gonna try to get it. So while it's doing that, anyway, let's continue. So I'll show you. I'll show you in a second. So we're getting the tokens, then we're updating the counter. The counter count the frequency of those words. So you can think of like we're going through the sentences within the data set, and we're creating like weight, like like, and we counting how much they okay. Okay, so it's still running. How much they okay. Then now we're gonna have this self dot fill for cup. So before we move on, I wish this was done, but it's not. I think it might take a while because obviously it has to get this, and this is my first time running this because I just created a virtual environment. So, but anyway, it's fine. So let's go to this fill for cup. What does that do, right? So we're going line by line, and we're not gonna miss anything, and you're gonna understand each and everything. That's for sure. So what we do is that, okay, this fill vocab does not take any input. Rather, what it takes is that it takes in the counter and it takes in the mean frequency. So you can think of like what we do is that a vocab contain all the weights, all the unique weights essentially in our data set. So right, let's say we have all the reviews, right? People are saying, I like this is nice, this is beautiful, the movie was awesome, this is great. So all these weights like awesome, great, we get them, all of them, we get all of them. And then because we have a counter, the reason we're passing the self counter is because we want only the word with the minimum frequency of 2. So I told you that, I explained to you that this self.counter count the number of words, how many times they appear. I said that, right? So for instance, okay, let's make an example. Let's say we have a word, something like something gibberish, like we never seen something like this. And this occurred once. So right, something gibberish like that. So this occurred once. Maybe something like awesome, right? You'll expect this in a review, right? So something like awesome occurred maybe 50 times in our data set. Then maybe we have something like nice, right? And it occurred maybe 100 times in our reviews, right? So that's what it does. This counter will do that. And this tokenizer, essentially what it will do, you see what it did? Essentially, it will take each word here. It will take each word and we'll just like tokenize it and create each thing here, right? So if like we had like two A's here, so it'll create these words, then then will create a counter of each word. So it will be like two here, like something like that, right? That's what this does here. Okay. So I hope that makes sense, right? So I'm gonna repeat myself before we go. This is going to create individual tokens, just like I showed you here, from the sentence. So it's like splitting the sequence by space. Then we update how many times they occur. Then this here, it's going to go through the sentences. Or where is it? Yeah, this, sorry about that. So this, we're going to have this vocab, which we we're taking it from the torch.text, we give it the counter, and we say the minimum frequency of words should be 2. So any words that have a frequency of 2 above, then that should be fine. The author also said that I think torch 11, you can use that approach to insert. You can use a you can use the specials here. So you can pass the specials in the vocab, so you don't have to do this. Meaning that you can define the specials and you can pass them directly. But anyway, so what we do here is that we have a vocab, right? You can think of like we have like all the unique words. But now we need to insert these special tokens that I told you about, like the class, the paired, the mask, the separate, the unknown. We're setting them inside the vocab. So how does this thing look like right now? So let's say now, for example, we have a vocab, like we have all the words, right? We have like I don't know, like data. We have like okay, this is a review. I don't know why I'm saying data, but uh, it's okay. So we have awesome, we have all of this stuff, right? Like we have all of that stuff, and these have been built up. That means that all of these words like have a minimum frequency of 2. But now at this position 0, what we say is that we're gonna add the the class special token. So this class special token was here CLA, so it's gonna be added here. Okay, so you can think of like we have a CLS at token 0, we have paired at token 1 and stuff like that, right? That's what we do there. Anyway, that's that. Let's go back. We're going line by line. We were here, we understood what this means. We're just filling up the vocab, right? That's what we do, like we're just creating our vocabulary. And then now we get into the pre-processing step. So we're taking our data set, we're saying self.ds, we're getting a review. So I repeat, this has reviews, right? Like we have reviews. So these are not sentences. Don't confuse this with this. So here we go straight to our data set. Let's remind ourselves. We are getting reviews. So these are still, it's a series, and we can loop through all the series. And this is paragraphs, not sentence, right? So I want you to always have that picture all the time, and so it's quite important. So we going through the reviews, then we split the reviews. So we know what this does. When we split the review, we get the sentences. So we get the sentences. So we say if the length of the sentence is greater than 1, right? So what we're gonna do, the reason we're doing this is because we want to calculate the next item and the first item. So you can imagine that if like you had only a review without the next sentence. Let's say, for example, I like a cat, something like this, right? So there is no next sentence here. There is no next sentence. We all know that. So we don't have to go through this because we're gonna get an error because we did not split this into 2. This what did not work because we did not find where we can split by full stop and space, right? So there was no that. But if there was like space, yeah, something like I also like etc, something like that, right? So etc, yeah. So you can see that we're gonna split by this, so we're gonna have 2 sentences. So that's why here we're saying if the length is greater than 1, and we can do the transformation. I know you don't know what the transformation is here, but just know that's why we do, right? So um then we go through that. Then we say for I in range of length of sequence minus 1, then we get the first and second, right? So we say the first the first the first sentence and the second sentence. So that's why we say I plus 1 here, right? So we get the first sentence and we get the second sentence, right? If this isn't confusing, think of it this way. So what's the length here? Let's say the length was 2, right? We say length of that minus 1 is going to be 1 because we have to loop once because of we're getting the first and the second, right? Okay, this might be confusing. Actually, let me do this. I don't know. Maybe it might not be, but let's just as always. as always, let's just go here. So for I in range of 2, so I'm gonna print I. So what we're seeing here is that we have 0 and 1, right? So what we're doing here is that we are saying that we have two sentences, but we want to loop through once because we're gonna get the next sentence by saying I plus 1. So we don't have to like loop twice. We don't have to loop twice. No, we don't have to do that. So that's why we say here, we say minus 1, right? We loop only once, right? Then what we do is that we're gonna access the next sentence by saying I plus 1. See, that's what this code does here. That's what we do. So we say minus that, then we're gonna get the next guy by doing I plus 1. So we're gonna go in the future. The loop does not have to go in the future. We will go in the future ourselves. So then we say npc and next sentence prediction. Then we say self.create. Right? What does the function do? Before we go to this function, I want you to make sure that you understand what we did here. Right? I hope you understand. I know you have. I know you did understand. I know that's for sure. So we go into this function now. We have nsp.append. What does this do? So nsp.append is going to append this. So it takes the first and the second and take one. So let's go to this function and understand what it does. So let's look for this function. There is he there. We find him. So essentially, we can see that we take the first, we understand this, and we take the second sentence and we take the target. We understood this. This is the first and second sentence within a paragraph. We understand. Yes, we do. So now we say self.process sentence. First copy. What does this thing do? Let's go. So don't worry, we're gonna backtrack to all of this. So I'm following all of these functions so that we're gonna backtrack. So you're gonna understand. Don't worry about it. So let's go now to this function. Preprocess process, right? There we are, we found him. So what does it take before we go to it? So we can see that it takes the first sentence. Okay, it takes the first sentence. What does it do with our sentence? Let's go to him. There we are, we found him. So it takes our sentence and it takes this should mask, which is true by default. That's why we didn't pass it in that function. We have inverse token mask, which is none. Then so if show mask, meaning that if we show mask, which is true, right? So what we're gonna do is that we're gonna pass our sentence into mask sentence. So your question might be, what does this function do then? So I know this might look like we're drilling into functions, but I think it's a good idea because if you think about it, if like we don't go into these functions and see what they do, then we're gonna treat everything as a black box. Then which means that we will never actually understand what is actually going on. So I think it's fine. Don't worry, we're gonna backtrack everything that we're gonna cover. We didn't cover. We're gonna backtrack to each of it, right? So now we just need to understand what this function does to the sentence that we gave it. So this is the function. So essentially, mask, like I explained, essentially the goal is that we're given a sentence, and that sentence it has tokens. So what we need to do is that we need to then mask certain words. Like 15% of the words will be masked, meaning that they will be removed and replaced with the mask special tokens, right? So what we do is that we take the length of the sentence and we loop through all the way to the max of optimal length or the length sentence, right? So essentially, what we're doing here is that we're creating inverse token. So you can think of like we're creating true for everything inside our inside this list here, all the way to the maximum length of the sentence uh, or the optimal sentence length. So what does this mean? It means that if like our sentence equals to 3, then the optimal sentence equals to 7, 7 will win. So it's gonna go to 7. So if the length here is 10 and the optimal is 7, then 10 will win. So we're gonna go all the way to 10. Okay, hope that makes sense, right? Then what we do now is that then take the length, we take the length, then we multiply it by the self dot mask percentage. So does this make sense? Yes, it does, because we are saying that we wanna mask like 15% of the length of the sentence. So we want the percentage of that so that we know the mask amount. So for example, what I'm saying here is that if you have a sentence, right, and the length of the sentence equals to 50, then you're going to take 15% of that. So that's what here we are doing here essentially. And we're going to say, okay, cool. This is the mask amount. So we're going to loop through all that, those weights that we have to mask for the length of those weights. Then we say random dot int zero length or length sentence minus one. So we're generating a random integer. So we say if random that random is less than 0.8, then sentence I is gonna be self dot mask. So else what we're gonna do is that we're gonna say j random dot rend. So we're gonna say 5 length of vocab minus 1 sentence I equals to self dot vocab lookup j. Okay, so let's take a step back and break this thing down. So one thing that we know is that if the random random is less than 0.8, then we're gonna mask this, right? Else, what we're gonna do is that we're going to, I think this random generates, I'm not sure, I think it generates 0 to 1 numbers. So from 0 to 1. So if we generate anything that is less than 0.8, then we're gonna mask. So we're creating some randomness to this, right? So that's what we're doing. Else, we're gonna create a random integer length self cup minus 1. We're going all the way to the silver cup. The reason we're starting at 5 is because we know the first 4 is those special tokens. So we want all the all the index within the vocab, right? Not the special tokens. That's why we're starting at 5. So just to remind you, uh, we can see that these are occupied 0, 1, 2, and are occupied by these special tokens. So we don't want that. We want the actual weights in our vocab, right? So that's what we do here. Then we're gonna say sentence I. So the sentence in this is gonna be replaced by the weight from this. So does this make sense? So essentially here we are we are saying from the sentence, just to sum up, from the sentence, pick any random weight. So that's why we're doing a random integer. So random weight. So that's what I mean, right? So choose any random weight from our sentence. And uh, if the random is less than 0.8, what we're going to do is that we're going to replace that weight with the mask, meaning that we're going to replace it with that mask token. Else, we're just going to give it a very any weight from the vocab. Okay, we're just going to insert any weight from the vocab. And then we're going to say inverse token mask equals to false. So which means that what this means here, what this means is that all the tokens that we're going to have to mask, they're going to be false. Does that make sense? Yes, it does. So anything that is not a mask is not going to be false. So that's what it does. So we return. Okay, so that's what this function does. So just to rephrase again, this sentence is going to mask our sentence, and it's going to make sure that it tell us which sentence from given the sentence, which one are masked, right, based on the true and false. So now let's go up. I told you that we're gonna backtrack. So where were we? We were here. So we know what this function does. We just went through it. We know that it's gonna return a list here of true and false. False means that we have to mask. True means that we don't have to mask. Then here it's a sentence. Yes. Did we do any transformation to our sentence? No, we didn't. Uh, that's we didn't do any transformation, right? Yes, this is the function. We didn't. Oh yes, yes. Sorry. We did because we replace the the weights at I index randomly so with the mask. So okay, so we can think of this guy here has changed. It has like those special tokens mask or randomly selected weight from the vocab. So okay, cool. Looking good so far. Then why? We take these and we pass them inside here. Can you see this? We say self.paired sentence and we pass them inside here. What's going on with this function? So firstly, let's try to understand this code. We say self.class. We add it to the sentence. So we add this class into to the first of the sentence, right? um, you're gonna see this a lot, especially in your deep learning journey. You're gonna see this a lot. This is a classification token that we add at the beginning of the token. So we're gonna see this a lot, especially in diagrams within the paper. So this is definitely normal, right? So just accept that. So at the beginning of the sentence, we add that. So yeah, it's nothing too crazy here. Then we take our inverse. Your question might be now, but Hector, wait, why are we adding true here? We're adding true because we don't have to mask this. Remember that this is contained true and false, right? And if we didn't add this, then the length of these two was not gonna be the same. Remember that this tell us where we have to mask, and now we just added this token to our sentence, so we have to say true. And this token we don't have to mask because it's a classification token. So it makes sense, right? But now the question that you might be having, it might be, but wait, Hector, what is this sentence? What does it do to this input? So let's go and figure out. So we know that this function here, it takes our sentence and it takes our inverse tokens, right? Inverse token mask. So this typing, you see that typing, it's at work. So it's just a handy function so that you make a code very robust. So so you can provide the type. So what you do is that you take the length of the sentence. Before we start with this function, just to remind you, we said pairing is that we gonna pair the sentence. Let's say our sentence, we have to pass 50 tokens inside inside our model. So now the sentence that we currently have, it only has it only has 30 weights. So we have to pad it, meaning that we have to like add that special token so that we get to 50. So maybe I'm not making sense, but let me try to explain to you. Let's say we have a sentence like take the length of a sentence. This is our sentence. Okay. This sentence here, we wanted to have eight, eight, eight the length of 8, but it's not currently. You see, it's 1, 2, 3, 4, 5, 6. So what we're gonna do is that we're gonna pair it paired, um, with that paired special token. So we're gonna do this. So now it's gonna be 7, 8. So now it's gonna be fine. That's what we want. But sometimes you are right. Yes, you are right. Sometimes it could be that the sentence is more, right? Let's say the sentence is more. Let's say see the sentence is more. Let's say maybe take the length of the sentence of the whatever, right? So now this is the sentence. Now we said we cut from 8. So you see that we're gonna have to cut this guy. We're gonna have to cut him because that's there's no other way because we're taking 8 and that's how we so we can see we're maintaining the length of 8 for each sentence. So that's what padding does. Before we get into the third, I should explain to you that so that we understand, right? So we say if the length of the sentence, you see here, we say if the length of the sentence, so it's greater than the sentence that we want to pass to the model, right? The optimal sentence. So we're gonna cut it. Do you see what I was talking about? We cut it. We said no sentence. You're gonna end from here because you are very long. However, if you are less, we wanna take your sentence and we're gonna pad you. So we're gonna pad you by taking this self dot sentence minus the length of the sentence. So here you can think of like we said, for example, taking our example, we said we have 8, then we said the length of the sentence was probably 6. So we have 2. So this is gonna be 2, which means that we're gonna say 2 times pair, then we're gonna add it to here. So which makes sense because then you're gonna take 6 plus 2, so it's gonna give you 8. So that's fine, right? Which means that this code here will look fine. So now we have inverse token must will be paired as well. So yes, this is true. So the inverse must will be paired, should be paired as well. That's true because of it has the length of the sentence, and we just trimmed this. So also it should be trimmed. Oh, I think maybe this was maybe supposed to be handled differently in a separate function, but that's okay. So what we do is that we say if inverse token mask, then if there's inverse token mask, what we do is that we take the length of this. Actually, we're doing the same thing. Actually, maybe this was supposed to be a function. Yeah, and because it's just the same thing. Anyway, unless if the author tried to check here for the token mask if it exists, but that's okay. That's okay. So, but it's the same thing that we're doing here. Instead here of checking the length of the sentence, we're checking the length of the token mask, right? So we're just gonna limit it, or else we're gonna multiply it. Here. So it's just the same thing, right? And remember that the sentence and the mask have the same length, right? That's for sure. Because yes, that's for sure. Because we're taking the length here. Oh, there's not. It's possible that they do not because if we restricted to be here. Yeah, it's possible. Okay, sorry about that. So it's possible for the inverse not to have the same length as the sentence because here we said we take the max of the length or the optimal length. So anyway, let's go back. So we do understand what this does, right? So we do understand, right? Because we retaining this sentence inverse. So these have been padded. These have a fixed length. Right? Anything that comes here have a fixed length that we want, and it has been masked correctly. Okay, so let's backtrack. I can't remember where we were, but I think we'll figure out where we were here. Yeah, I think we were here. We went here because we went to get those masks. Yes. So now we done all of the processes, right? Let me just make sure that we. Yes, that's correct. We done all the processes. Then we're returning the first mask with the updated sentence. So now we know what is inside here. We know that this sentence contains a mask and it contains a fixed, meaning it has been paired. And this first mask is just a Boolean list, which is telling us which index have been masked based on true or false. And then we pass in the two sentences, right, that we had. We put them inside here, then we get them here, like so. Okay. Then what we do is that we take in the updated first, then we say self. Like I told you, still remember that I told you that we're gonna separate this two. So this is the next sentence prediction. So we take in the updated first, we add in the self dot separate token, which is a special token. Then we add also this the second sentence. Okay, I hope this makes sense, right? So now what we do is that we say self.vocab lookup indexes. So we're gonna look up for indexes of this sentence here. Okay. Then what we do is that we say inverse token mask. We take the first mask, we add to true, and the second mask we add we add true here, including the second mask. Okay. So because these are list, and this is a list of true and false, so we also add this true. So which means that this, yes, it makes sense because self dot separate is true. So we don't have to mask this. So I think, yeah, inverse token mask, yes, this is correct. Remember that we have to maintain the same length of the sentences on the mask, and we have to make sure that where we don't have to mask, we add true. So that's what we're doing here. I hope guys, I hope like you guys are understanding me, because I'm not sure, like maybe I have to kind of like improve my explanations. But yeah, I hope you do. But I'll be happy to get your feedback, so that I know if like I'm explaining something good or something not good. But anyway, let's continue, guys. Let's continue. So we create sentence item without masking random mode. So we say self dot process sentence, which is the same function that we called. Then we pass the first copy, and show mask equals to false. So here it looks like we're creating the first and second word, but here we don't mask anything. Right? So we're still creating the same procedure that we did, but here we don't mask any words. Okay, so if self.show include text, then we pass this. Uh, did we cover? Yes, I think this is because of the debugging. Yes, I think it was because of that debugging sentence that we did. Okay, so we pass in these um, SPS sentence, then we return all of this, right? And then else we return this. Okay, so I hope this makes sense. So we're returning the next sentence. We're returning the next prediction indices that we pulled up from our vocab. Then we have original next token sentences. Uh, yeah, I hope this makes sense. Okay, so let's backtrack. Yeah, let's just try to go back and see where we were. We finished this function. We did explain this function. We did explain this function. Where we were. Okay, we were here because we had to call that self.create. So nps.append. Okay, now we see what we are appending. So now you see, it's nice. It's nice. I feel like it's nice actually going through like this, because now when you come back, you understand what actually has to be inside here. Because we understand now what is actually has to be inside the NSPS. We do understand. Understand that okay, it has to take all of this, the next sentence, prediction sentence, the indices, the original, the inverse token mask, all of this stuff, right? We know what this stuff mean, right? So we know what is inside this list, and now what has to go inside here. It's just a set of those transformation of those sentence transformation. Then we say false uh, next sentence prediction item. So we say self dot select false next prediction. So here, just to kind of like explain to you before we go to the function, we're trying to select the false sentence, right? Meaning that we know that we said that the next sentence prediction is to predict if the next word, the next sentence, so I meant to say, is is the one that is following. Meaning that when you write a paragraph, right? Like the next sentence has to follow, right? So now, so sometimes we have to like create fake sentences that follow. So which means that they're gonna be false, meaning that the next sentence prediction has to predict false. So that's what this function is trying to create. So we're gonna go to that and see how that is working. So there's it here. So essentially it takes the length of the sentence, as you can see here. Then it says random.randint. Um, so it says we're generating a sentence index given the length from 0 to all to the sentence length, right? Then we set next sentence index. Then we also doing the same thing. Then we say while next sentence index equals to sentence index plus 1, next sentence index equals to dot uh, random int. We select in random value here. Then what we do is that we take in the sentences. Then we say sentence index, sentence, and sentence. next sentence index. Does this make sense? Yes, it does. So essentially what we do is that we generate an index, right? So let's go back. I want to show you something before we go there. So we give it a sentence, right? But the question is that where is this coming from? Because here we're saying for I in index, so we're giving it sentences. Where is this coming? Okay, sentences. So it's a list. Okay, it's from our data set. Remember that here we said we're generating the sentences of the whole entire data set, right? So yeah, I think I was confused here. I was confused at this function. What is it doing? But yeah, now I understand. So essentially, we're getting all the sentence from our data set, right? Then we're getting the length of that. And so now it makes sense because we have to generate the index from you can think of from all the sentences. Like let's say we have 1 million sentences in our data set, we generate an index, like meaning any number because we randomly want to select a false state. We do the same thing with this, right? But like random, it's possible maybe even if it's one in a million, but it's possible that they might be the same. And we don't know. We don't want that, meaning that they might be following one another. So what we do is that we check if the current index equals to the next index equals to next index plus one. So if this is the case, then we have to generate another random value. It's possible that even here we can get the same random value. So you see, actually it's a while loop. Okay, so that's fine. Actually, it's a while loop, so it's gonna make sure that it comes out when these are different. But anyway, just to explain to you guys in a much better way, let's say you have 0, 1, right? We know that that sentence is holding all the sentences in a sequential manner. So what happened is that if we don't want anything that is sequential, right? Because now if it's sequential, and this false non sentence it becomes it becomes like clueless, like not clueless, but rather worthless, not necessarily something of great value because we want something that is false. So that's what we're doing here. And we return the sentence index, which is then we say sentence dot next sentence index. So we return this sentence here, it's false. It's not the second sentence. So that's what we do. Hope that makes sense. Hope that makes sense, guys. I hope it does. So here we understand what this we have here. We have the false second sentence and we have the first. Then we say self dot tokenize uh the first and the second, right? We tokenize these, then we say np dot append self dot create first and second, which is we're gonna pass it zero here. So this is just to differentiate between one and zero. So here we're gonna get the tokens of these. Okay. Then when we're done, we can take NSP, which is a set that we pass in the columns. So does this make sense? So let's try to understand it. So it's gonna take this is a data, right? This is contain all the next sentence. This is contain all the next sentence indices, or all the original next sentences, all the original next sentence indexes, invest token mask, target. Then we are creating a data set from that. Then the columns are gonna be these guys, and these guys matches, right? It makes sense now. That's why I told you like I'll like come back to these columns so that you understand. Now they make sense because we can see that these are all the columns and they matches our data that we have been going through and transforming, right? So that's what we have there. So is there anything to explain? I think guys we're done here because we returned the DF. Let's see. I think we explained everything honestly. Yeah. Yes. So well done, guys. Well done. If you've made it to this far, we have understood everything. We have understood each line of code. We have break it down. We have understood, right? And that's like the goal of this. And I've gave you the intuition behind why we're doing this and what's the intuition behind it. So now let's go to the model. We're gonna look into things like attention. We're gonna look into things like join embedding, and yeah, then we're gonna go into the trainer and we're gonna understand how they work. So the first thing that we're gonna do is that we're gonna import all the libraries that we're gonna use. Um, we're gonna see how they're getting used in this case. Then we're gonna assign the device to GPU or CPU depending on if we have a GPU, else it's gonna be a CPU. This is the same thing that we did also in the data set. um, then what we're going to do is that we're going to initialize this class with the vocab size and the size. So you can think of this vocab size as like the number of unique tokens in the vocabulary, whereas the size essentially represent the number of dimensions in the embedding vector for each token. So essentially, maybe this might be confusing. So let's do this. So the vocab size, you can think of it as like contain all the words like all the words, our words. It could be word, it could be token. You know, I'm just creating all of these words. It could be weight, whatever it is, right? Let's say we have all these words. So these words are coming from our data set of reviews. Then we have the size. So the size essentially represent the embedding vector of each token. So you can think of this word it's represented as a token. For instance, let me say the first weight has like these numbers here, representing this weight here. So something like this, right? So you can think there's a comma, obviously. Yes, there's a comma here, but that's something like this. I think there's actually these values are actually small, but that's essentially the idea. Now, what they mean by size is that they mean the size of that vector. What is the size of that vector? For instance, we instantiate this embedding. So, for example, let's say our data set, all the weights in our data set, like there is like 30,000 weights. Then we say that the size of the vector of each token of each weight. So I'm going to use the token and weight intangibly so that you understand. Then we can say here maybe it's going to be 128, something like that. So that's what this means here. Okay. Then we create this token, self token embedding. Then we have this self segment embedding. So before we start, you can think of this self segment embedding essentially is going to essentially create a segment whereby we assign all the first sentence to zeros, the second sentence to one. In the first data set, we spoke about first sentence and we spoke about second sentence. Now we're gonna assign these to zeros and these to one. I think it will be a good idea for me to show you a visual so that you have a good understanding of how this works. So looking at the input, right, the first part, the pinky part here. So we know that we put this the class at the first. We did this. We know this. Then we say my dog is cute. Then we separate, showing that this is the second sentence. Then he likes to play with whatever. Then we say separate. So we understood this, right? Then now we have this token embeddings. So these are token embedding. We're gonna embed these tokens. This is what I was showing you now. Then we have this segment embedding. So segment embedding, essentially you can see that the first sentence is gonna have A, and the second sentence is gonna have B. Can you see this? So essentially what this means is that the segment embedding essentially is going to help us to differentiate between the first and the second sentence, you see? So that's what it does. Then we have a positional embedding, which is we're going to get into, but it essentially gives the sentence uh, each token a position. That's what it means. So, but that's what this means here. So, because of you can see from the image that everything has the same length, so that's why here, even the segment we initialize it to have the same length with the token embedding. So now we have the embeddings, we have the segment. So we're gonna normalize the size. And what do? We take in the inputs tensor, right? I'm not sure, but I think The input tensor is going to have the dimensions of batch size and sequence length, right? Let me write this down so that if we make a mistake, we can come back and batch size and sequence length, like so. And what's happening is that we take this, then we say give us the last um, dimension. So we can see that it says size. So this is the sequence length, right? So that's what it is. Then we have this function here. We call it attention position. Essentially, this is positional embedding. So this is like this part here. You see this white part at the bottom. That's what it is. Essentially, if you don't know this, but the goal here is that we give each token a position. Like because we're working with like sentences, like they are sequence, right? So each word like has a position in a sentence, and then we pass in the self.size. Just to remind you, the self.size essentially is the dimension of the embedding. Then we pass in the input tensor, which is going to be this input, which is, I think it's going to be a batch size by sequence length. But the question that you might be having is that, but how does this? I do understand that it gives a position, but how does it work? Uh, it so before we go to this, I know that I don't like to skip any line of code, but before we go to this, I think let's finish this, then we're gonna focus on this function, so that for now just think of it as like it give each token a position within the sentence. Then we get positional tensor here, like so. Okay, so you can think of this as like just to make an example. I think we learn well when we can see a sentence. So let's say I like a cat. So you can think of this as like it's gonna return a tensor saying that I like is at one, I is at one, like is at two, uh, a is gonna be three, cat is gonna be four, just like that, right? So we have this here. Okay, that's what it is. It does. We're gonna understand like there's quite a lot of interesting things that are being done here. It's not being done like one, two, three, four. It's more complex than that, but we're gonna look into it. Then here what we do is that we initialize our torch.zeros. Yes, because what we do is that we take the sequence, the sequence length, which is the input torch.zeros. We take the input tensor, we send it to the GPU, and we create. This is like we create this. We take the shape of this, which I said that it has to be the batch size and sequence length. Then we create zeros. All right, right. I hope this makes sense. So essentially, let's try to understand it. So let's say we have a batch size and we have like some sort of like a sequence like one, two, three. So essentially we're gonna create zeros inside here. But for the dimension of this input, right? For the dimension of that input. So it's gonna be zeros inside here. So this like here means that use the shape of this. Then here we say segment tensor, then we say sentence size uh, integer division 2 plus 1 all the way. So this might be quite confusing, but how does it work? Okay, so like I like to kind of like make an example. Let's go to our example notebook so that you understand. I think it's also good because you get to understand PyTorch. So it's good for also learning. So what I'm gonna do is that okay, we already imported NumPy, so I'm gonna say input uh, just to make a dummy example. Then we're gonna say np.array, right? Then we're gonna say array like so. Then let's create some sort of like a two-dimensional array. So we're gonna say um, two-dimension matrix. Then we're gonna say these are zeros like so, right? And we create another zeros, which is another row. And we're gonna see zeros. Then we create another row. which is gonna be zeros, zero, zero, zero. Um, uh, yeah, it's just yeah. You know what? I'm just gonna paste this because the way I'm doing it is just not good. Because I just wanted to see for you to see, right? Like I'm just gonna paste this example here. So anyway, you can see that here we have input dot shape. So we have four rows, like four rows, and we have six columns. 1 0 0 0, right? So now I want you to say this is equal, this is three, this is three, they're equal. So now I want you to set these ones to zero, all of these ones here to zero, right? So what you will do is that you will take the input, right? So you set these ones to zero, you set these ones to one, right? So you know there's a segment. We spoke about this. We said that this one is going to be represented by zero, this one is going to be represented by one, because this is the next sentence, this is the first sentence, okay? So how would you do that? You will say, I want to select all the rows. That's what you do, is that you select all the rows, meaning that everything that is inside here, select it. I want to transform it. Then you're gonna say input dot shape, because you wanna take in the last, like this is number six. Then you're gonna say I'm gonna divide that by two, because you want to go from the half side. Then you're gonna say equals to one. Okay, so this might be confusing. Let me repeat this. So you selected all the rows, but from the column you don't want to select all the columns. You're saying from half of the length of the column, from half. So what is the length of the column is six. We got it here. We selected it here. Here we are selecting six. So we say six divided by two is gonna be three. So starting from here, right? Starting from here, so you can think of here we are writing something like three, right? So that's what we're doing. We say starting from here all the way to the last element. So you can think of in Python when we do this, we're going all the way. We don't write anything here. All the way, you will know all the way. Set that to one. Then now if I bring the input, so we should be able to see our transformations are done. You see, there is it here. You know? Understand? So that's how it reads here. So that's what the segment does here, the segment tensor. So now this is should be easy now. We get the tokens, we insert our input size. So now what will the dimensions be? Because we know that the tokens essentially is gonna the tokens take the vocab and the size. So essentially, what all this do is that it will take the input, and then it will create this dimension for each token. Does that make sense? So I said that. Okay, let me make sure that you understand this. So I said that my assumption was that we have a batch and we have a sequence length for this input. So what all this do is that it will then for each it applies, yes, it applies across the last dimension. So what it will do is that take this last dimension, then it will apply this function, and then this function here, it will return the the embedding, which is the length of 128. So here it's going to be the embedding vector, like so. So and we add the segment and we add the position to this, then we return. Hope that makes sense, right? But if you forget, just think of this picture here. What we did now, we just did this picture here. That's what we did. So now, as promised, I said that I'll explain to you the positional embedding, which is basic, which is this here, which is this function here. Okay, so let's try to understand this function now. So, um, so what we do is that we take in the input tensor and the dimension. So we did see this because we provided the self.size, and I did explain that the size essentially referred to the vector or the dimension of the embedding. This, and then it takes in the input tensor, then the input tensor at the zeroth element there is a batch size, and then at the last element there is a sentence size. And we did actually predict this because we said that there's a batch size and a sequence length. So this is actually correct, as we can see that they are being extracted from this. So what we do here is that we're creating a range of the sentence size. So you can think here what we're doing is that we're gonna create a range from zero all the way to the to where the sentence length, the sentence size is. So for instance, let's say the sentence size is 49. So that's what we're gonna do. So it's gonna be 1, 2, all the way to 48 because of we're starting to index at 0 here, like so. Okay, so that's what this torch dot range does. And we just make sure that the position essentially is loaded within a device. But essentially, there's a position of each token within the sentence. Then the dimension, we also do the same thing within the dimension. Like I said, that the dimension here could be some sort of like it's a hyperparameter that is passed in. So let's assume that it's 128. So we want to represent each token with the dimension vector of 128. So you can imagine that we're gonna have also like a range from 1 to all the way to 127. So I'm saying 127 because we're starting at 0 here. Okay, so that's what we have here. So then we have that. I think that is to we normalize this vector of the position of this dimension by dividing the this this range by the dimension. Okay. Then here we have this position dot and squeeze. So you can think of we taking the position, which currently has the dimension of the sentence size. Then we add another dimension of 1. So for instance, let's say we had 49 as our sentence size. Then we're gonna add 1 like so. So we're gonna have 2 dimension like so. Okay, then we take the position, then we divide this by a small value, then we square it by the dimension, which is this. So you can think of this equation right here. So we're trying to simulate this equation right here. Then what we do here is that as part of the equation is that we have to apply the cosine and sine uh, within the we apply the sine within the even, and we apply the cosine I think within the odd. This code here will do that. I know this might sound confusing, but we can break it down. So essentially, what you're looking at here is that we're taking the position, right? We take the position and we say, let's just make some sort of like an example, shall we? I think we should, because that way we get to understand much better. So, so let's just create a symbol of like a dimension. So I'm just gonna take in the np.array. So we're gonna have 1, 2, 3, 4. Actually gonna have to create I want to create let me do this. Let me just create let's have to create as many rows as possible. Create 2 like so. You know, coming up with examples sometimes can be hard, but it's fine. Then we can say 4, and we're just gonna print uh, input. Then we're gonna say dot shape. So we have 4 rows. Yes, we have 4 rows and 1 column. which is what I wanted because here you can see that if we go to the model, where is that we're saying that take the position which is currently has 49, 49. We said it's 49, but it's the length of the sequence. Then we add a dimension one. So that's what we replicated here. So you can think of this as the length of the sentence. Then we added this dimension. So what do they do? Just to analyze. So what we do is that we said across all the rows, we then uh, then we want to apply this, which means that we want to apply this jumping by two. So this is like the movement. So I'll explain it to you now. But anyway, let's just do it. So I'm saying across all the rows, right? I want to apply this across all the dimensions. So I'm just gonna assign this one so that we get to see the results. Yeah, this doesn't work, and which means that which is true because we're saying that all the rows, right? And then we say within the columns, all within the columns. So, but the column is only one column. So this is not legit. So now this I'm starting to question this implementation here. I'm not sure if it's me, but this here, let's say we have let's just try to understand this. Let's say we have 49, which is our which is our sentence size. Then we add a dimension and squeeze here. We're gonna add a dimension of one, right? That's what we're gonna have. We're gonna have a two-dimensional matrix from position. So this is what I replicated. We can think of this as like uh, it's the same thing. It's just that I have four values instead of 49 because obviously we're making an example. So I'll say that how this was supposed to be implemented is that you're supposed to say across all the column, but within the row, what you want to do is that I want to move by two. See, it works. So you see that we're applying within the even, we're applying one. So we're jumping by two. So here it's one, then we jump, we don't apply, we apply one, we don't apply, we apply one, we don't apply, we apply one. That's what it is. So that's what it is you were supposed to do. But the intuition here is that this is how the formula is like, guys, right? So this is how the formula is like. This is how we're trying to do. We essentially you can see 2i plus 1. So you apply the sign across the even, and you apply the cosine, I think, across the odd. Okay, and this is what we did here. But the thing is, I'm not 100% sure about this implementation. Maybe it might need me because I can't see the dimension, but I think this was supposed to be applied across the row. I might not be 100% sure, but based on the implementation, it looks like this is what we're supposed to do. But anyway, that's okay. What we have here is that we're gonna apply the sine across the even, right? We apply the cosine across the 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 odd. If I go here and I put one here, you'll see that now one was applied at even, now it's gonna be applied at odd. See, there's one here, there's one. Here it was always one, so don't mind this one because it was always one. So if you I see I change it to 10, it's not gonna apply because it only applies here, right? That's what it means. So yeah, hope it makes sense, guys. So position expand, essentially we're just getting the batch size. So we just like getting the same output with the input, so that's fine. And that's what we did here. That's what positional embedding is, right? I hope you're not gonna forget it, but yeah, that's what it is. But anyway, now I'd like us to get into the attention here. Yeah. So now looking into the attention head, essentially we taking the dimension input and the dimension output. Then we're gonna linearly project these query and key and value. So we create this linear layer of like it's gonna be the dimension input and dimension output. Then what we do is that we're gonna have the forward pass whereby we take in the input tensor, right, along with the attention mask. Then we're gonna pass in the input tensor across the query key and value. Okay, then we calculate the scale, which is going to be the last dimension of the query squared by zero point 0.5. Then this is going to be used to divide the dot product between the query and the key. Okay, doing a dot product between the query and the key, we're going to get the scores. So there's this function called um, batch matrix. Essentially, it's going to it takes in the batch and then it takes in two matrices and then it do a dot product between those two matrices. I think that's why it's called BMM. So this is gonna take the query and it's gonna apply the dot product with the key here. Okay. Then what we have here is the scores. We apply the attention mask if it is given. If it is not null, then we fill those where we have to apply the mask, we fill that with this very small number, then we get the scores because of we did the dot product here. Then we apply the softmax uh, across the last dimension. Then we got the attention weight. Then we take that, we multiply it with the value weight. We do also do the batch matrix to get the context. So if an attention, just to repeat, if an attention mask is provided, then it is used to mask the scores, tends up replacing the mask position with the negative, very negative value, very small. The softmax, then it's applied across the last dimension of the mask, mask scored tensor to obtain the attention weights, right? Then what we do is that we then compute the weighted sum of the value using the attention weight, okay? And that's like then we return this. So I hope that makes sense. Then the last thing that we do is that we have this multi-head attention. So you can think of like each weight is going to have the query, key, and value. So what we need to do is that we need to then project these across the different heads that we have. So number of heads is a hyperparameter that we specify. So for instance, we're gonna say for I in range of number of heads, then we're gonna create the attention for the number of heads. Then what we do is that we create this linear layer whereby we take the dimension output by the number of heads. Okay, then we have the output as the dimension input, right? So then we return the self.norm dot layers. So a linear layer in this case, you can think of it as like we're trying to map the concatenated output of all the attention heads, right, to the input dimension. So the the each attention is gonna, because we know this is a linear layer, so each attention is gonna return the dimension output, right? Because of it's a linear layer, so this is what the output will be. But because of it has been it has been it has been routed to all the number of heads that we have, so we want to concatenate all of that. So that's why we doing this. Then the output is gonna the dimension of the input, right? So the dimension of the input, even if you can watch the transformer video, you'll see that we consistently keep the dimension input across because we're gonna have a forward pass. We're gonna have a feed forward that it's gonna take this dimension. So hence we need to maintain this. Then we have layer norm. I think in recent papers, what they do is that they try to apply the layer the layer norm before some of the layers. Based on that, I think they say that actually they're getting better accuracy. I'm not 100% sure, but yeah. Anyway, what we do here is that we say for head in self.head. So you can think of we taking this um, attention head. Okay. Then what we're gonna do is that we're gonna pass in the input tensor and the attention mask. Then we get the scores. We say touch.concat s dimension minus one. So we're concatenating everything inside here. Uh, then we call this the scores. Then we say linear scores, which makes sense, right? I think this is quite intuitive because what we do here, because we're doing touch.card, we know that each head has a has an output of dimension output, right? But because of we concatenating these, so we concatenating them, so we have to multiply this by the number of heads. So that's why this here, the linear layer makes sense. That's why here the linear layer is going to have this dimension here. So we pass it this score. So it's going to give us the scores. The scores have this dimension of input. So we apply the self.norm, which is the layer norm. Okay, so that's that. So we have a multi-head attention mechanism. We have the attention mechanism. Now we're applying the encoder part. So the encoder is the full thing. So usually how you, if you're first time seeing this, essentially how you can think about it is that we have within the transform architecture, we have layers and we have sub layers. Then a layer is like an encoder, right? Then you have sub layers, which is a multi attention and feed forward. So now you can think of like this encoder, it's going to bring all of these pieces together, like all of this stuff together. So all of these sub layers. I think of it that way, right? So you can see that we bring in the multi-head attention. So we give it the attention heads. Like I said, this is a hyperparameter. In this case, it's 4. Then we have the dimension input and the dimension output. Then we have the self feed forward. Like I said, that hence here we needed to maintain the dimension of this. Hence here we see that the output has to have the same dimension because that's what, if I'm not mistaken, yes, you see. So the feed forward takes the dimension input. So hence we needed to maintain that. Then we have the dimension output. Then we apply the NN dropout. We apply the KLU, which is a smooth activation function. Then we have a linear layer and dropout. Then we finally have a layer now. So this essentially is another sublayer. All this is a sublayer. All this is a sublayer. So encoder has two sublayers. Then we apply the sublayers here. We just call them and do a forward pass. We return the normal layer. So essentially what we're looking at is just the transform architecture. Hence I say if you watch the transformer video that I created, you'll know what's going on here. Okay, now we bring everything together, right? We have the joined embedding. So now like it's like everything, the data set, everything, embeddings, we bring them together, right? So we have the join embedding, which is gonna take the vocab and dimension input. So, and we're gonna get the self embedding. Then we take the self encoder, which will take then the dimension and dimension output and attention heads. Then we have the self token prediction layer. We have the softmax, we have the self classification layer. Then we do a forward pass, whereby we're gonna take in the given the input, we return the embedded input. This is this, so we know that this it's gonna return this. So it's like the the input has been added, the segment has been added, the position. So we return in this. Okay, I hope we did not forget that. So we have the embedding, then we have the encoder where we pass in the embedding, right? And we have the attention mask. So what is the dimension of the embedding? So that's my second question. We know this, right? So we're returning the output here, which we said it was the batch size and the sequence length. right? But because of here we added the token, so we also have the embedding size or the vector, right? So that's what this will be here. Makes sense. Then we have the attention mask. Then we know what will be the output here. It will be the input self attention. Then we passing this encoded into the token prediction. So your question might be self dot token. So it's a linear layer whereby we pressing the input, the dimension input, and the vocab size. So like I said, I think we're gonna predict the we're predicting the mask tokens. What's next? Then we see first word encoded, and we return the softmax of the token prediction and this classification layer. So yeah, I think that's that. So I think yeah, here's the classification, and I think this is a classification of the next sentence. This is the token prediction, the next token prediction, the mask token. Um, yeah, and that's what we're doing. So I did explain these, like what the purpose of this is. In the when we started, that's what we're trying to predict. But yeah, I think that's that, guys. I tried by all means to kind of like give you an overview of this. Um, but yeah, so this video is quite long. So I'm even thinking of like I'm gonna try by all means to kind of like go through the trainer now. So I don't know if you guys don't like these long videos. Let me know. I will try to create short videos. But yeah, for now, let's just look into the trainer and see how these models are trained. So I'm just gonna go straight to the trainer. We'll come back to the functions as we go through the trainer because of anyway we call these functions. What we have here is that we have the model. So this model essentially is coming from the bed. So what we just did right now, okay, and then we have the data set, which is coming from the data set. If we go back to the data set, I don't know if you guys can still remember, but this is what we started with. So we call in this class. So we have the batch, which is the batch also is like a hyperparameter we define, which is in this case 24. Then we have the epochs, how many times we should go through the entire data set as we train. Then we create a data loader, which is we create a batch. Then these are all the checkpointing and the summary functions. I don't think that's quite important in this case. Here we have the solve criterion, which is going to become the what's this? The sigmoid binary cross entropy loss. This is mainly because this side we have this what is it? The self classification layer because we have to do the next sentence prediction. Okay, so we have this loss. Then we have also the negative log likelihood loss. Um, Also because of here, if you can take a closer look on the model side, we have this self token prediction layer, and this is not a binary, it's a vocab size, whereas this self classification is a binary. So here what's going to happen is that we're gonna predict the token, the must token. Then we have the torch, the optimizer, which we in this case we're gonna be using the atom with the learning rate and weight decay. What's next? So yeah, that's that. And these I think it's just for like if we go in through the training, we get the model summary, the training length, the vocab size. So yeah, so I wouldn't pass anything that is very important. So anyway, what we do here is that we have this function called train, which is going to take an epoch, and then we're going to say we're going to go through the loader, which is going to be the loader. We get the batch within this loader, we get the batch, and then from this batch we get this data here. I think this looks familiar. You still remember this? It was the same thing that we did from the data set, just to remind you, so that we make sense out of all of these things together. So these things here, because this is where we finally left, right? And this was like the what we stored into our data set. But now you can see that we're retrieving these things, right? Uh, just want to make sure that you understand that. Then we have the self.optimizer dot zero grid. So essentially here, for every mini batch during training phase, we want to set the gradient to zero before starting the back propagation. So this is because we don't want PyTorch to accumulate the gradient on the subsequent backward pass. Okay. Um, then we have the self.model. So this self-taught model, just for your reference, essentially is the model that was coming from the model that we just covered. So it's this model bed. So, and from this model, what are we getting after we pass in the input and the mask? We get the token. I think this was supposed to be tokens because we're trying to predict in tokens, if I'm not mistaken. Then we have the next sentence prediction. So if we go to the model, we can see that these are the two things that we're returning. So we can see that we're saying solve.softmax token prediction. So we are saying that uh, that's why I think it's token predictions. So we are saying that we apply the softmax across the token predictions, which tokens have been predicted, right? Then we have the soft classification layer. What is the next sentence prediction, right? And uh, which is a binary classification. Okay, uh, I hope that kind of like makes sense. Then we have also the inverse token mask and squeeze token mask, which you're gonna. I think this is just to shadow the mask token in the model output. So the reason is that we only training we only training the model to predict only mask tokens. Okay. Then we did explain this ML criterion, just to highlight that, just to make sure. Yes, that negative likelihood. So we did explain that. Where we so we accumulate these losses. So we take the loss of the token, right? We take the loss of the next sentence prediction. So we add it to the overall loss, which is here, right? Then we do the same thing for the average NSP loss. We do the same thing for the average mask loss. Okay. Then when we're done is that we update the weight, we do loss dot backwards, and we update the weight, which is self dot optimize dot step. Um, yeah, I think that's that, because all of these are just like printing the logs. So I wouldn't like go too much hard on ourselves with these, because we just like getting the accuracies and saving the checkpoints and saving the models and stuff like that. But I wouldn't like literally go hard. I think the most important thing was this. But that's like the whole entire idea. Uh, I think this was quite interesting. I won't lie to you guys. Um, to see like the whole entire thing coming together. And now it makes sense. Like every time we're gonna see bait being used on Hugging Face or whatever, the good thing is that we have idea now of like how this stuff work, right? We can understand what's going on under the hood, how this was trained, what was the objectives, and stuff like that. So yeah, I really appreciate it, guys, for tuning in. I'll create this video covering the code and going line by line in such a way that you guys actually get to understand in much depth. So yeah, thank you very much, guys. I really appreciate it. I'll see you in the next one. Thanks. Bye.